It's Mr. T here, and we are here to talk about electronegativity. Electronegativity is something that we can use to determine how ionic or covalent a chemical bond is. So we're looking at electronegativity as the difference in the pull of electrons between two different atoms when they are chemically bonded. And that's going to be based on the atomic radius and the strength of that nuclear pull. So electronegativity is the tendency of one atom to pull on the electron of another atom when they are chemically bonded. So each atom is going to pull on the electrons of the opposite atom, and you're going to get a little bit of a tug-of-war. And electronegativity is a measure of that amount of pull. It is on a scale from 0 to 4, and it's called the Pauling scale, after Linus Pauling, the famous physicist. And 4 is the strongest possible pull that an atom can have on electrons, and 0 is the weakest. The difference between the pull of the atoms will result in whether that bond is ionic, polar covalent, or non-polar covalent. So we classify chemical bonds into these three categories: ionic, polar covalent, and non-polar covalent. So this is a chart of electronegativities. Now take a look at this and take a second and think about, like, do you see a pattern here in the electronegativity values on the periodic table? Take a moment to think about that. What do you notice? You'll probably notice something similar to the other periodic trends that we've talked about, that the number is the lowest down in this corner here with the atoms that have the largest radius, and it gets higher and higher as we move toward this corner with the atoms with the smallest atomic radius. And that makes sense when you think about the smaller the radius of the atom, the closer the nucleus is to the electrons. And the closer the nucleus is to the electrons, the stronger the pull that nucleus will have. So the atoms up here in this corner up here have the highest electronegativities. Now, you may note that the noble gases have small atoms, but they have 0 electronegativity. And that's because they can't make chemical bonds. So here's another chart looking at electronegativity. You will notice that the atoms that really stand out are fluorine, oxygen, nitrogen, and chlorine. Those 4 atoms have really high electronegativities. So they really hold on to the electrons in a chemical bond. The atoms with really weak electronegativities, these are your alkali metals. Those atoms are the largest, the electrons are furthest from the nucleus, and so their electronegativity values are really low. So let's define what these 3 kinds of chemical bonds are that we were discussing. You've got ionic bonds, which represent a near total removal of an electron from one atom to another. You can think of it as one atom literally stealing the electron from another. You have polar covalent bonds, which are electrons that are being shared between 2 atoms, but they are being pulled more strongly toward one than the other. So they are being shared, but they're not being shared equally. And then you have non-polar covalent bonds, where the electrons are more or less being shared equally between the 2. Here's how I like to kind of give an analogy for this. Imagine that you have a candy bar, and you've decided that you're going to share the candy bar with a friend of yours. In a non-polar covalent bond, you split the candy bar almost exactly in half. You're both getting equal quantities. You give it to each other. You're sharing it. In a polar covalent bond, you break it off maybe 2/3 to 1/3, where you get a lot more of the candy bar than your friend does, but you are sharing it with that friend. And with the ionic bond, you simply steal the candy bar. You get it all, they get none. So, how do we determine whether these bonds are going to be ionic or covalent? Well, we look at the difference in the electronegativity. The greater the difference, the greater the difference in the pull, the more ionic it is. The closer those 2 numbers are to each other, they're able to pull with equal force, the more non-polar covalent it is. So it's a sliding scale. There's no definitive, like you're now ionic, you're now covalent, but rather we describe it as more ionic or more covalent because it is this sliding scale. So we generally say that when the difference between the electronegativities of two atoms is greater than 1.6, we say that it is an ionic bond. When the difference is between 0.4 and 1.6, we say that it is a polar covalent bond. And if the difference is less than 0.4, we say that it is a nonpolar covalent bond. So greater than 1.6, the pull of one atom is much stronger than the other. We say that's ionic. If it's 1.4 to 1.6, we say that it is somewhat stronger, so the electrons are being pulled more toward one direction than the other, and we say that it's polar covalent. And if the difference is less than 0.4, we basically say the pull is equal. When the same element is bonded to itself, like oxygen to oxygen, nitrogen to nitrogen, fluorine to fluorine, then the difference in electronegativity is zero because they have the same electronegativity, and that's automatically a nonpolar covalent bond. Okay, so again, there's nothing special about the numbers themselves that say this has to be ionic at 1.6. 1.59 is polar covalent and 1.6 is ionic. Rather, it's a gradient where basically we describe the behavior as being more ionic or more covalent. Okay, so let's just summarize real quick why there is this difference in the across the period. So as the atom gets smaller, the electrons get closer to the nucleus. And since they are closer to the nucleus, the pull on the electrons gets stronger, and therefore it is able to pull those electrons closer to it, and therefore we say that it has a higher electronegativity. So if you were to take sodium and chlorine and put them next to each other, chlorine has a much smaller nucleus than sodium, even though they're in the same row, and therefore the electrons, as you can see on here, are going to be pulled more toward the chlorine than they are the sodium. Okay, so here's some examples on here. So you'll notice that the carbon-carbon bond has the electrons being shared exactly equally because they have the same electronegativity. So we'd say that the electrons are basically sitting right halfway in between the two of them. That would be a nonpolar covalent bond. In the sodium chloride, the difference is 2.23, which is greater than 1.6. So the electrons are sitting way closer to the chlorine than they are to the sodium, to the point where we basically say chlorine has stolen the electron and it becomes a negatively charged ion. Sodium has lost its electron and becomes a positively charged ion. You can think of it like a tug-of-war. And it doesn't matter exactly who's in the tug-of-war, whether they're little kids or big NFL football players. What matters is the difference in the electronegativity. So if you were to have two elements with really small electronegativities, two weak atoms, if you will, when they do the tug-of-war, the rope may not move, and we would say that that is a nonpolar covalent bond. They're both small, and they're both at about equal strength. However, take this kid and put him up against an NFL football player, and the difference in electronegativity is going to be enormous, to the point where when that NFL player pulls on that rope, the kid's going to go flying. He's going to lose the rope. So in this case, you've got these little kids against these big adults. In this case, we know who's going to win this tug-of-war. The rope's just going to get pulled right away from the kids. But if the two sides are equally strong, like saying putting two sets of NFL football players against each other, you may end up with the same result as you did when two little kids were pulling, which is they're equal in strength, therefore it's nonpolar covalent, the rope doesn't move.